Yes, so thank you for coming here. With the microphone is better but I could do without. So thank you so much for being here. I mean, I know a lot of people might go just after this to this, to the manifestation that is happening here. So this is really hot from the press, right? I mean, that just came out. So for sure, if you go there after my seminar, you will know. Yeah, it's in Folha right now, okay? So you will know this, so you don't have to worry about that. So, well, anyways, I'm going to focus for the next, like 45 minutes or so on organic and inorganic interfaces. So these are the weakly bonded interfaces that I alluded to in my title, and they are quite interesting systems that they hold the promise of really hot applications. And these are just some examples of experimental work that you can find in literature recently, where this prototype of organic and inorganic interfaces are used for several different things. For example, you can build a system that is a graphene sheet with some functionalization by organic molecules, in which you get a really, really specific biosensor for certain proteins that you can even implant in your teeth. Or you can control the voltage of a molecular. You can control the voltage through a circuit through a molecular switch, and even look at the conformation of this molecule through Raman spectroscopy, or even tune the electronic transport through a junction by functionalizing it with peptides. So all of these examples are examples of technology that use these inorganic parts and the organic parts together. And the promise there is that you will achieve cheaper, less toxic, and more versatile technology in the future, right? But already, 20 years ago, this Nobel Prize, Herbert Kromer, he already said the interface is a device, and here is particularly true, especially for these new types of interfaces with organic and inorganic materials. And this field faces many challenges, most of which lies on achieving control and predicting the function of these new types of interfaces. And I particularly look at that from a theoretical point of view, and I'll give you a little bit of a more or less pedagogical introduction in what I will want to calculate today. Yeah? So one of the things I want to calculate is the average of a certain quantum mechanical observable at a certain temperature of choice, for example, in the canonical ensemble. And this is given by 1 over the partition function that here I call Z, and then the trace of this, what we call the canonical density matrix. Beta here is 1 over KBT, the Boltzmann constant times temperature. H is my Hamiltonian, A is my observable, my operator A that I want to calculate this.
We're assuming equilibrium already.
Yeah, this is in equilibrium for now, exactly. So, to calculate that, you need to at least solve this nice quantum many-body equation, which is the Schrödinger equation. And as I hope all of you know, this in principle depends, in my case here, in all degrees of freedom of electrons and nuclei, because these are what matters in these cases for these materials. And this is not really solvable, because you have the exponential scaling with the number of degrees of freedom, and you can't really treat this problem up front. But especially in these types of interfaces that I was talking about in the beginning, you can't deal away with saying, maybe I don't do quantum mechanics here, and I'll do just an approximation with a classical Hamiltonian or something. And that's a very bad way to go, because the fundamental interactions that stabilize those systems are inherently quantum mechanical. So they are stabilized by things like hydrogen bonds, which depend on the polarization of the electronic cloud, or van der Waals dispersion interactions that depend on instantaneous dynamical dipoles that appear in the electronic density. You have charge transfer on the interface when you put these things together, so electrons hop here and there. And also the nuclei present quite a few nuclear quantum effects, because you have a lot of light nuclei. These are hydrogens, and hydrogens do have quite a quantum mechanical nature, even at room temperature, as I hope to show in my talk here. Okay, so what do you have to do? You have to solve this many-body equation. And here I just show you the Hamiltonian, so the many-body Hamiltonian that we have to deal with. And here, this big I goes through nuclear degrees of freedom, small I through electronic degrees of freedom. And that's that. And well, I mean, you can't solve this right there. So you do some approximation. So everything I'll do here today lies on the following approximations that I will tell you about. So first of all, I always do the Born-Oppenheimer approximation. The Born-Oppenheimer approximation tells you, well, what if you can decouple the degrees of freedom of your electron? Yes, sorry.
You've already made an approximation.
Yes.
The nuclei are points, right?
No, sorry, not necessarily. I mean, these should be all operators here. I'm sorry, yeah? So in the Hamiltonian here, they should be all operators. These Q's and R's are all operators that then will act on something that is the full wave function, if you like.
Things like dipoles and things like that?
Well, they appear, this is the Coulomb interaction, right? And the Coulomb interaction should then go, they will give rise to all of that. Yeah, exactly.
The magnetic moment. You can have magnetic.
Oh yeah, yes, of course. I mean, and then spin also and all that. But yes. This is yes. Okay, so yeah, exactly. So the Born-Oppenheimer approximation is just, you say I can decouple the degrees of freedom of electrons in nuclei, and then I end up with two separate Schrödinger equations in which an external potential appears in each side of this equation. So for the nuclei, there is an external potential coming from the electrons, and from the electrons, there's an external potential coming from the nuclei. And then you can just solve these separately. It is analogous to saying that your wave function is separable, right? In one, it's one for the electrons and one for the nuclei, and you can multiply them, and they give you your full wave function. And then you have two problems to solve, the electronic problem and the nuclear problem. So the electronic problem, you also typically have many electrons in your system, and this would already be impossible to solve the Schrödinger equation again up front only for the electrons, even if you have that. So there is this theory that's called density functional theory, which is very famous and many people use. And the reason why it's very famous is that it maps all of these many-body problem into expressions that depends only on the electron density. And the electron density is a quantity that no matter how many particles you have in your system, only depends on 3 degrees of freedom, x, y, z, if you like. Yeah? So you deal away with this exponential scaling by casting everything in terms of the electronic density, and it has been proven that you can really get your full quantum mechanical ground state energy if you just know the ground state electronic density of your system. Yes.
I'm not from this field.
Yes.
Just a simple
yes.
question. Do you have the exclusion principle in this Hamiltonian? Is it?
It comes from the symmetries of the wave function in that case, right?
Okay.
So, yeah.
So it's implemented because of. So you have.
So sorry, in the DFT, or
So
yeah.
You have some information that the electrons are fermions somewhere.
Yes. You impose that on the wave function. You have to impose. Yes.
It's not at the level of the Hamiltonians, at the level of the wave.
Yes.
Okay.
Yes. Is it? Well. Now, yes, I would say yes, but I have to. Yes, exactly. Yes.
Somewhere.
These questions are the worst, But yeah, so I mean, typically you. Yeah, I know, because exactly. So typically, for example, if you start from this Hamiltonian and stay within wave function methods, you have to do an ansatz for a wave function that is a Slater determinant. So it has this the anti-commutation, so the fermionic nature inside.
Well, okay.
No, exactly. So, well, anyways, we can talk about that.
Yes.
So no,
Yes,
it's there.
Yeah.
No, because in fact you can have a solution which is a
Bosonic. Yeah.
Solution, but then the fermionic part is in the spin part, which is
Not there.
There's no spin part there. There's no.
Yeah.
But you have to put it afterwards.
Yeah.
Yes. The wave function.
Is a fermion wave function.
Yeah.
So you pose that as opposed to
Yeah.
Well, I mean, on the Barn-Oppenheimer approximation, the nuclei become just an external potential, nothing. So they're just an external potential. This term becomes, then they become just point particles, which give you an external potential depending only on the position. So then the equation depends parametrically on the position of the nuclei. So you don't do it. So now the nuclei are nothing for the I mean, it can be whatever you want at this point. So it's just an external potential that comes from somewhere, and you can do some approximation with the nuclei that the Barn-Oppenheimer approximation doesn't tell you what to do with the nuclei or the electrons. You could treat the electrons classically or quantum mechanics or whatever, and you could also treat the nuclei classically. It just says I can separate them because of the time scales involved in the process. So the idea is more or less that since the nuclei are so much heavier than electrons, you could justify that terms that couple them don't you know, there's an adiabatic separation basically on the.
Are you trying to minimize the potential with respect to the nuclei also?
And so it depends. No, I mean, so in density functional theory, what you do is that you take. So you see, this is actually the functional that you minimize in the end. It depends. So given a certain configuration of nuclear positions that you can do anything with, then you just minimize the electronic problem. That's all, exactly. So this is what you do, and this is, you can solve density functional theory in the Consham scheme. This is what is done in this case. So this is the total energy, total quantum mechanical energy, and here's my electronic density. And then you map, what you do is you map your problem into a system of non-interacting particles that you know how to solve. And then in this system of non-interacting particles, you know how to write the electronic density. It's just the sum over the occupation numbers and the square of the Consham orbital, so the square orbitals of this non-interacting system. And then all you need to do is solve this system of single particle equations that is given here with these potentials. This Vx is exactly what comes from the nuclei at a certain position. And Hartree is just the Hartree term of the Coulomb interaction. This is the kinetic energy of non-interacting particles. And then you have this something here that you call the exchange correlation potential. And the exchange correlation potential is given by a functional derivative of the exchange correlation energy with respect to the density. And this is where all the unknowns lie. So here you include correlation in the kinetic energy and also correlation in the Coulomb part and the exchange terms and all that are all included in this piece here. And this is what has to be approximated. So in DFT, maybe if you have ever heard any talk about DFT, you'll have heard some acronyms. And all these acronyms, they refer to which approximation you're doing for this exchange correlation potential that you have here. That's great, but as I said, then you have what do you do with the nuclei? I mean, this is fine. They just come in here as an external potential, but you have a choice to treat nuclei as classical or quantum mechanics.
Sorry,
yeah.
There's no way to map the first problem, the Hamiltonian, this correlation potential. You said that you use approximations. There's no way to map what you have in the first line to.
No. No.
So using another formula from scratch.
Well, yes, sort of. So you can, depending on your system, it's possible. So if you have a Gillium electron gas, then you can do that. Then you know exactly what this term should look like, right? Or well, a system of non-interacting particles also, or some homogeneous electron gas. You also know how to do some of that. So you have these systems that you know the answer for, that you map something on the other. But for a general system of real many particles, no, because otherwise you would have to solve the many-body Schrödinger equation. You can't do that, right? So you can't do a map one-to-one. So you know these limits, and you know some mathematical limits, because you know some systems where you can solve at least parts of this. And then these functionals, they try to interpolate between these limits or make some approximations that, you know, like obey some sort of things you can know about. So that's how you come up with approximations to that. But there's no, the thing is that you need to have a functional form that depends only on the density of all these interactions, right? So, and that's what you don't know.
Yeah.
Yep.
Yeah, but in here just the equations.
Yeah, we're not talking about nuclei now. This is just electrons.
So, but when you wrote this Hamiltonian, you wrote the kinetic terms for the nuclei.
Yes. But then I do the Born-Penheimer approximation. Then you end up with an electronic Hamiltonian that is separate, right? So.
But are you neglecting the third term? There's a potential between the nuclei and the electron, right?
Yeah, this,
so
yes.
What is that in this NH formula? Which there corresponds to that?
It's this external potential.
Okay.
Yeah.
What is phi I?
It's the Kohn-Sham orbitals. It's orbitals of a non-interacting system that just happens to yield the same density as a real interacting system would have. Yeah. So you map your whole problem into a system of non-interacting particles that will give you the same density as a real system of interacting particles. And then you just optimize these orbitals in order to get this density. So the only thing you can get out of this scheme in principle are densities that will then give you a total energy or something like that. Yes.
This is electronic density.
Yes, electronic density, exactly. Yes. Okay. So now maybe I go to something that you might have heard about. So for the nuclear problem now, so what I do to include nuclear quantum effects then is path integrals. Yeah. So these are Feynman path integrals. You might have heard about them. They are used here in a little bit different way than it's used in particle physics, for example, because we discretize these paths, and then you end up with these ring polymer formulations. So what is done here is that so I already start with something like a partition function in equilibrium, right, at a certain temperature, inverse temperature beta here. And I know that this is given by the trace of this canonical density matrix. And then if you go through the math and you do a Wick rotation where you go to Euclidean space-time, then you end up mapping the system into a system and discretize the space, yeah? So then you end up with these ring polymers. And then your partition function, the exact partition function of your quantum system is given by a classical system, a classical ring polymer, when the number of beads of this ring polymer goes to infinity, and the Hamiltonian of this ring polymer is given here in the bottom. So here you see that you have these spring terms that connect two beads of these ring polymers. This comes originally from the Euclidean, the kinetic energy part of the Euclidean action. And then the potential here, which is summed over all the beads of this ring polymer. This potential is, for example, the Born-Oppenheimer potential that comes from our electrons. Okay. So this is where these things, so it comes as an external potential here also. And in this case, because I'm doing, I will do path integral molecular dynamics, you have the freedom of introducing back these fictitious momenta here in this Hamiltonian in order so that I get a Hamiltonian, otherwise I would have only a mapping of the action here. And this is our fictitious momenta that you introduce in order to be able to sample this phase space with molecular dynamics, which is something I would like to do. So what does that mean? It means that if I have a Hamiltonian now here, I want to be able to write equations of motion for this Hamiltonian in that I can evolve my particles in a fictitious time, which is not real time, and then I can sample this phase space so that I get averages based on this on the sampling of this partition function that I have here. And this will be the real quantum partition function. You see that these force constants depend on h bar. This is where basically quantum mechanics come in. In practice, I mean, so then again you beat this exponential scaling. Yes?
What's capital N?
Sorry?
What is capital N?
Capital what?
N. What is it?
The number of atoms. The number of atoms in your system. The number of nuclei.
What is omega small n?
It's this. 1 over, so beta n is n over kt. N is the number of beads on the ring polymer.
So that should be beta. So why? Just n over beta over n?
It's kt over n h bar.
So why is
Square.
it that way? Why isn't it just beta over n?
Huh?
I just don't understand your notation. Beta sub n means
Is n over kt.
so it's just n times beta.
Yes.
Oh, okay. It looks like it's a substitute.
Yeah, it is. but it's just a notation, I'm sorry, yes. It's the usual notation.
Don't have different temperature devices.
So no, exactly. But in practice, what happens is that each beat evolves at the temperature n times t. So it's 1 over n kT. It's 1 over n kT. So it's 1 over n times beta.
So each beat has a different temperature?
No, they all have the same temperature.
But they evolve at temperatures?
Yeah, exactly. So each beat, they all evolve at the same temperature, which is n times the actual physical temperature of your system. And n is the number of beads in the ring polymer. But it enters with a 1 over n also here in the Hamiltonian, you see. So this is also beta n, and then so that doesn't diverge, right? In practice, what happens is that each atom, and this is for many atoms, each atom in your system becomes a ring polymer. So what happens is that you have many, many replicas of your system, each one living in a different imaginary time slice. And these imaginary time slices are connected by these harmonic springs, as you have here. And since it's always something in equilibrium, you get a partition function and all, at time, imaginary time beta h bar, you get back to the beginning, right? So it's cyclic. That's how you close the ring polymer, okay? I'm not going through the maths because I don't have time here, but it's very straightforward. So there's no approximations there. Except, yeah.
Continuous version is just the usual free Hamiltonian?
Yeah, the continuous version is the usual path exactly. It's the exact same formalism, except you don't have this term usually here. This is just a fictitious term that you can put in because it's quadratic. You can always do the integral of a Gaussian out and in. And that's just there in order to have a molecular dynamics type of formalism that you can do with it.
Maybe you just said I wasn't paying attention. So why is it? Oh, I see. So it's a closed loop because you're...
Yeah, because the paths have to start and end at the same point. Because it's yeah.
Was it trace?
It's a trace. It's a trace. Yeah.
Because it's finite temperature?
No, it's because it's a trace. So if you do the trace,
Okay.
yeah.
Okay.
So in what sense this is a fictitious momentum? Because the nuclei, they have some physical momentum. Sorry.
Yes, the nuclei, of course, have some physical. So the real momenta are, so the quantum kinetic energy comes from these terms, okay? So the spring terms are the quantum kinetic energy.
Why there's no kinetic term?
It is here. So imagine now that you have the continuous version and that all the imaginary time slices become really, really, really close to each other. This here is a derivative, right, with respect to imaginary time. And this is exactly the Euclidean, it's the kinetic energy term in the Euclidean action, and this is the potential energy term in the Euclidean action, exactly. So then you don't need this here, but if you put it in this formalism that you discretize and you want to simulate numerically with ring polymers, you could stop here and you could do Monte Carlo to sample that. That's fine. Path integral Monte Carlo also exists, but it's not very efficient because you're usually not interested in energies very far away from your minimum. Molecular dynamics is nicer because you stay in the minimum and you sample more efficiently the terms that actually contribute to this type of partition functions. Okay, so one thing to say is that, as I said, you do something like molecular dynamics, but you have no evolution in real time. It's instead only a technique to sample this phase space. So there are approximations in real time that I might have time to get to, I might not, but so let's see.
There's no evolution in real time because it's
It's always this trace that you do, so you stay on the imaginary time axis. Okay. So we develop codes to do these things. So these are two codes that we developed in my group because even though you can beat the exponential problem of Schrödinger equations, it's still very, very difficult to treat these systems. And if you don't have really large supercomputers and very efficient codes, you can't do that. This thing here, this code deals with the electronic structure part, so it solves the Kohn-Sham equations, density functional theory, and so on for the electronic problem. And this code here deals with, for example, path integral methods and or anything that moves nuclei in time. So the outline of my talk is that I'll give you a little bit about how the problem of finding structure in this type of systems, then the problem of self-assembly, how electronic and nuclear degrees of freedom do talk to each other. So we have, of course, problems where these electron-phonon coupling, so the electrons and phonon degrees of freedom couple in your system, and then I'll talk very little about time evolution itself. So this here is a system that could be a black hole, but it's not. And so it is the porphysine molecule. The porphysine molecule, the formula is given here, on a copper surface. So it's copper 111. These are actually scanning tunneling microscopy images of two isomers of this porphysine molecule, because it doesn't matter what happens here too much, but you see that it can exist in a conformation where hydrogens are on the opposite sides of this cage or the same side of this cage. And this type of experiments, they can image these two isomers, and they can see which isomer is the lowest in energy, because if they put energy inside the system, they can have a transition from this to this. But if they just hit it up, it goes back to this one. So this trans isomer that we call is the lowest energy conformer on the surface. And this density functional theory that I talked about in the beginning, as I said, has a bunch of approximations that you can do for that exchange correlation potential. And one thing that you need to look carefully at systems that are large and you can't benchmark within theory itself, is how good these approximations are for the problem you're looking at. So this wasn't a publication that's not from our group, it's another group in the literature, where they looked at a bunch of these approximations. These are all different approximations for that exchange correlation potential. And they looked at which one would give this conformer lower in energy than this conformer when it's absorbed on copper 111. And everything that gives a negative sign here in this column is wrong. It gives this conformer lower than this conformer here. This one here is apparently correct, but there's something wrong with the distance with respect to the surface, so it's a strange result nevertheless. They also find it strange, they don't trust it. And so they conclude, well, density functional theory doesn't do a good job on this case, right? And we wanted to look at this system for other reasons that will become clear later in the talk. And we took the two conformations, the cis conformation, the trans conformation that they had, and we tried a bunch of other approximations of this exchange correlation potential, and we confirmed what these people had seen, and we also found no other functional that could give the right answer there. Yeah? And then my PhD student started getting a little bit suspicious of that, because when density functional theory fails, it typically fails. Each thing gives a different answer. And this was giving a very consistent answer to the wrong side. Yeah? And so the problem there was actually that we were not dealing with the correct structure. And this structure was around in the literature. It's indeed easier to get to, because this other transconformer that we found is more buckled with respect to the surface, stays at another site on the surface. But it happens that even though this molecule is quite rigid, it has actually a rich conformational space. And when you get to the bottom, to the real lowest energy structure, you see that they are isoenergetic with a certain functional, or indeed lower in energy, so the correct energy ordering that is also observed in experiment. Yes?
So what is the difference?
Yeah.
Just the position?
It's the position. Yeah, it's the position on the surface, because it's if you would, so this is 111 surface of this metal, right? So each atom here is not exactly equivalent, because below it the structure is different, right? So when so the electronic structure of each site is a bit different. So there are equivalent sites, but not all of them are equivalent. And when you move, you get different interactions of the electronic structure, and that's what creates also this buckling. So in this case, I'm just treating the nuclei as just classical things that you can just move, and then at each position you minimize the electronic problem, and then you try to move with an optimization algorithm until you find the minimum energy structure also there. So this is a problem where, the theory was actually okay, but the structure was a problem. So this, when you get to big systems, you need to take care with that in order to go forward. And this is even a rigid molecule. For much more flexible molecules, you have a much more complicated problem, because the conformational space becomes super large.
But
These are
structure, you cannot find a structure by experimental methods?
It's very difficult. So you see, I mean, they see this. They know when it's trans and when it's cis. But this is it, right? I mean, look how many atoms you have. I mean, it's very hard. And when they can image, and these are one of the best experiments, one of the most resolved experiments you can do on this type of systems. And it's quite good. I mean, but it was a single molecule, right? But it's not atomic resolution. It's very difficult to get atomic resolution. Even if you do, typically you don't resolve both the molecule and the surface at the same time, so you still don't really know where exactly in the surface it is, and then you can resolve only the surface and not it's a mess.
So you're predicting structure then?
Yes, exactly. So then, I mean, or you can do other things. You can do vibrational spectroscopy also in experiment, and then also do vibrational, and then try to match that, but like seeing it, it's very difficult because you see only electrons in the it's very difficult. So exactly, so you can predict the structure, and predicting even more flexible molecules is much more difficult. We do that also, but I will not have time to talk about that. Instead, I'll give you just a little bit about what happens. This was an isolated molecule, so what happens when you have things like self-assembly of molecules and you have interfaces between two types of semiconductors, one of which is an organic semiconductors. And that's what I alluded to in the beginning of my talk. So you can have, for example, electron transfer from one part, the inorganic semiconductor, to these molecules that lie here. And this simply happens because these molecules are strong electron acceptors. So if you have the valence band maximum and the conduction band minimum of your inorganic semiconductor here, and the corresponding, if you would like, valence band maximum and conduction band minimum of this organic part at much lower energy, this is an empty orbital in this part here, so it would like to accept electrons when they come together. And one of the problems with density functional theory, again, is that depending on this exchange correlation functional that you use, you predict a different ordering or a different difference between energies of these levels that can lead to spurious effects, and one has to deal with that. So one problem of density functional theory, for example, is that usual functionals that you use, they have a problem called self-interaction. So that means that one electron can actually interact with itself because the exchange term is not exactly included inside these functionals. And this leads to a bunch of problems, including the spurious charge transfers, but you can correct for that in several functionals as well. They become a bit more expensive, but you include some part of these, what we call exact exchange. So you really include the exchange of the electrons inside the functionals as an operator in this case. And that is where you get better descriptions because you mitigate this error. So the calculations just become a bit more expensive because you're lifting some approximations that you have, and then the challenge is doing a big system with this type of more expensive functionals. So in that case, for example, here we could do even several layers of these molecules and predict some properties of that because you have two causing molecules, one that is a little bit smaller and one that is a little bit bigger. It just has an extra benzene ring. And we had a collaboration with experimentalists where they measured exactly these two systems that we're dealing with here. So this is hydrogenated silicon 111 surface, and these molecules are called F40CNQ, so it has a lot of fluorine atoms, or F60CNNQ. And one thing that you can see is that, long story short, the molecule-molecule interactions within a certain layer is much stronger for this larger molecule than this smaller molecule here. And this leads to a situation where these molecules have a much larger tendency to clump together than these type of molecules here. And when they do, these are atomic force microscopy, so a different technique than what I showed before. So this is just looking at the height of the surface, very close to the surface. And what they see is that when you have the smaller molecule, they see a kind of a smooth coverage of the surface, but when they have a bigger molecule, you see big, tall islands. And so we can, basically what theory, the role of theory in this case is to explain what is the physical interaction that gives rise to these differences between the two molecules, and here in this case, is really what we call van der Waals dispersion interactions that are much larger in this case than in this case, even though they're quite similar. But more interesting than that, I think, is how the nuclear structure interplays with the electronic structure. So this is what we call electron-phonon interactions, and here I treat it in the adiabatic limit because I'm still doing the Born-Oppenheimer approximation. But let's say I would like to calculate an electronic structure property like the work function of my material. So the work function is the work you have to do to kick out an electron of your material out of it. But I would like to calculate that at a certain finite temperature where my nuclei are not, they have a structure as well. So they have some type of wave function, if you like, and then some type of distribution at finite temperatures. So within this approximation, this would be simply, again, this trace here of this electronic work function that I call phi in this case, which will be depending on the position of the nuclei. And then this Hamiltonian that enters this partition function here is just the nuclear Hamiltonian in this case. So I already calculated the expectation value with respect to the electron, the electronic wave function. That's what gave my work function. And then I have to calculate now the expectation value with respect to the nuclear function because they are separable, right? So if I make the assumption that I can treat my nuclei as classical particles, so they are not quantum at all, then it's easy. My problem is just calculating, its usual classical thermodynamics. It's just calculating the average of this work function given a classical Hamiltonian from a nuclei. And already there, I mean, this is what we find. So you see that you have a change from when you turn on temperature, it's not the same value as you would have if you calculate just one single static structure. And for one layer and two layers of these molecules on the surface. But more interesting than that, I would say, is that you have a very broad distribution of these work function values that is much larger than KBT at this temperature that would be 300 K. So if it was just a thermal broadening of this quantity, you would have a width of this distribution that was basically KT. KT at this temperature is about 25 millielectron volts, so 0.025 in this scale, and you see actually something like that is more like 0.5, so it's quite a lot larger.
How do you get the work function from that expectation?
Oh, no, the work function I have to have calculated before, and this comes from solving the density functional theory problem, exactly, and that's how I calculate it.
But the nuclear, what you're saying is that the nuclei affect the work function.
Correct.
Yeah,
so in that case, what I did is I computed this term here, yeah, and I computed this with molecular dynamics. So what I do is that I know the Hamiltonian. It's a classical, in this case, just a classical Hamiltonian for the nuclei. I have equations of motion, and these equations of motion will sample then this ensemble because it's consistent with at this temperature because it's consistent with this, and I put a thermostat connected to this.
How this fits back to the density function?
Exactly. So the density functional theory part you need in order to calculate the work function of your material. So what I do exactly in this case is that for each position of my nuclei, I solve again the electronic structure problem, and I find the work function at that particular position of the nuclei. Then I evolve my nuclei in time with these equations of motion given by the external Born-Oppenheimer potential at a certain temperature that I set with a thermostat that fixes the temperature of my simulation. And then at this new position, I solve again. And then I solve again. And then I solve again. Yeah, but it can be done. So these are movies, actually, of the simulations, you see. And what causes this big distribution, these very wide distributions, are in fact that you have this very wide, so it's very soft, so it's weakly bounded, so you have these very wide fluctuations, right, of the nuclear degrees of freedom. And this creates that. Not only that, it creates this shift of the average of the work function. That does get closer to the experimental saturated value, and you see that if you put more and more layers, you also start to saturate this work function. So there's an interplay between these two.
As you said, these are just thermal fluctuations.
These are thermal fluctuations.
Now you're going to do quantum fluctuations.
Correct, yes. So exactly. So these are just thermal fluctuations. My nuclei are not even quantum yet.
So how do you know so you know the masses of all the particles?
I do. I know the masses of all the particles, and I also know, let's say, the electronic structure of all atoms, right? I know how many electrons they have.
You figure out what that B is also?
Yeah, so then I have the interaction between the electrons, right? And this I approximate with density functional theory. And then in this case, my nuclei, the interaction between the nuclei, they are just classical particles. So they are simply, yeah, particles that have whatever, a mass.
Cool.
Yeah, yes, yeah, exactly.
So they're not
Exactly.
particles you fit. You
Yeah,
know
I know them, exactly. Okay, so these simulations involve typically, I don't know, 150 atoms in a unit cell in their periodic simulations, but that's about the size of that. Yeah.
Does the answer converge as you take n to infinity?
No. So what n? So here my nuclei is two classical particles. I'm not doing this path integral stuff yet. So I'll do it next.
Okay.
So exactly. So then what happens if I want to make my nuclei quantum now? Then the simulation becomes a lot more costly than what I had before, because I not only have to solve those equations for one replica of my system, but many replicas, because I need many beads, and these beads are replicas of my system, right? So in that case, I have many replicas of this 150 atoms, so it's 150 times n replicas that I have, and this can become very expensive. So it does converge. So it typically converges. It depends on your system. It depends on the highest phono mode that you have in your system because of quantization of phono modes in this case. And the higher it is, the more beads, the more replicas you need to converge. The lower the temperature, the more replicas you need to converge. But typically, for this type of systems, about 30 replicas is converged. You can see the convergence. You can just look for that. But 30 replicas would be a lot, so you'd like to use less. And you can do smart tricks, especially in this case that you have a weakly bonded system. You can say, well, hydrogens here I have only on my adsorbates here. This is already a water molecule attention, and not on a heavy metallic part that I could have in my system. So I can treat nuclear quantum effects only here and not here, because here they might not be that important. And then you can do a smart thing here that in the end, you end up treating the full system, the big heavy system with many atoms, taking only a single replica, here P prime, which is, I'm sorry, the number of replicas here is now P and not N, but this is the number of replicas of your system. And this is much less than what would be the full amount of replicas in your system that you then treat only for the adsorbate that's typically much less atoms in this case, and so on. This converges very nicely. Of course, if you take P prime equal P, you go back to the exact Hamiltonian, and the errors that you make are very small, maybe 0.25 milli-electron volts per atom, even if you make the harshest approximation there. So that saves a lot of time, and then you can do a lot of nice systems. This, again, this work function, but now I would like to calculate it really from quantum mechanics. So this is now, indeed, as the number of replicas goes to infinity, now I have this ring polymer partition function here, and what I need to do is calculate an average, but now on the extended phase space of this ring polymer. So you have n times your physical positions, n times your physical momenta, and so on. And you measure this work function at each bead, at each replica of your system. And then you see what happens. I mean, indeed, there is a certain effect also in these work functions. This is now water molecules adsorbed on a platinum, a 1-1-1 surface. This is a system that is quite interesting for water splitting reactions and electrochemistry as well. And you see that now this is what you would get at finite temperatures with classical nuclei and with quantum nuclei. So you have about a 0.2 electron volts change on this work function, and this is actually relevant for people that are looking at applications of that. The reason for that is that actually the dipole moment of your water molecule changes when you consider the nuclei to be quantum particles, because they can delocalize in certain directions more than others, and you change this dipole. This dipole is what interacts with the dipole on the surface and what ultimately gives you the barrier that your electron has to feel to pop out of your system when you try to get the work function of the system. There are more funky effects, so that has not been measured before, but other things have been measured. So for example, when you see isotopic effects on electronic properties, this is a clear sign that your nuclei are quantum particles, because for example, if you have hydrogen or deuterium, hydrogen and deuterium have the exact same electronic structure. So only from the electronic structure point of view, there can be no difference on an electronic property of this atom. But if you measure something, then this means that the nuclear part is mattering for that, right? And if you see here, so this is again a measure of the work function. This is a molecule called cyclohexane on a rhodium-111 surface. And you see that in experiment, they measure the work function at different coverages of the system, and they see a difference when they have the cyclohexane completely deuterated or completely hydrogenated. And they don't quite know the origin of this effect, but if we calculate from this path integral molecular dynamics, this is again the distribution of the work functions here on the top, you see that we see a shift. And we are simulating at a slightly higher temperature, because for us it's very hard to simulate at the same temperature that they have. We would need a lot more computational power. But we see a shift here of 25 milli-electron volts in the same direction as in the experiment. And this is now what we call a difference in the pushback effect. So the electronic structure of the adsorbate pushes back the electronic structure that tries to spill out of the surface. And this happens differently if you have hydrogen or deuterium, because hydrogen can delocalize more strongly in the direction of the surface, get closer to the surface, and that doesn't happen with deuterium. So this is something that we get really nice agreement with the experiment, and we're moving towards really looking at these effects. This had never been simulated before. People didn't know what to do it. Just experiment could do it. And this is something that involves now systems of 250, 300 atoms or so in order to have a unit cell that makes sense. So we're getting there, and we're explaining new things. This is all still on the static part. And then I would like to maybe use 5 to 10 minutes just to talk about how do we measure then, how can we simulate time-dependent processes that happen there, so response properties of materials. And response properties of materials now, if you look at linear response theory, they are often related to a time correlation function. So time correlation function is again in equilibrium given here, so you can, you have fluctuation dissipation theorems and all that you can think about, but so what you have to calculate now is not only the operator at time 0, but also some operator evolved in time. So now you not only have to solve the time-independent Schrödinger equation, but also the time-dependent Schrödinger equation in order to get this time evolution. And now you get into a realm that starts to get really difficult, because if it's hard to solve this, it's even harder typically. What this gives, so why is it important? For example, one thing that we would like to do is measure the vibrational spectra of something. So this is the water molecule, attention H2O. And you have really nice potentials that were fitted. So let's say I don't have to care about the electronic structure right now, because I have very exact potentials there. And I would like to calculate the vibrational spectrum of these water molecules, the nuclear vibrational spectrum of this molecule. This is given by the Fourier transform of the velocity time correlation. This you can prove in a couple of ways. And this is not, you're not making any approximations here, you're just calculating really the Fourier transform of this. You have this time evolution exactly from the trace and all that, so depending on how you calculate that, well, you should get the exact answer. But I can also, for this particular molecule, because it has so few degrees of freedom, I can actually solve numerically the Schrödinger equation for the nuclei exactly on a grid. And then the answer that I get is these dotted lines that I get here. And if I calculate the vibrational density of states doing this time evolution with classical nuclei, not quantum nuclei, then I get what is in blue here. So there's something missing, and it's always missing more at higher frequencies. So these are frequencies here, and this is what we call quantum enharmonicity. It really comes just from the fact that you're neglecting the quantum nature of your nuclei. So within the path integral formalism, you have a problem, because now you're in the imaginary time axis, and you would like to calculate something that is real-time evolution. And you could do that. You could think about doing an analytical continuation back to real time, and that is horrible. That doesn't work, because you have errors that explode. It has been tried, but it's not yet there. So you need, for high-dimensional systems, right? So you need to use something better than that, and what is better than that? Well, you have to rely on approximations. And approximations based on this path integral formalism are quite appealing because they let you treat systems that are really large. So one such approximation that I proposed when I was working in Oxford with David Manolopoulos, who is really one of the experts in this area, is that it's based on a theory that he had proposed before, in which you take the time evolution in the extended phase space of this ring polymer as meaning real-time evolution. And then, this is just an ad hoc approximation, and then you see, if you calculate correlation functions in this extended phase space, do they obey certain limits that make them sensible? And they do. They obey limits that are, for example, the harmonic limit they obey the high temperature limit, and short time expansion limits they also obey. So you can only hope that they give you also a nice description within this limit. So very, very recently, like 2 years ago, there's a new theory that gives some idea of why this type of ad hoc approximation works at all, that you can then derive from real quantum dynamics. But originally it was proposed really as an ad hoc approximation. And it had some problems to calculate vibrational spectra specifically. This is what I worked on, solving these problems. I will skip this part because in the interest of time. But the point to take is that in these approximations, the main approximation that we're making is that we're completely neglecting quantum coherence. Yeah? So quantum coherence is neglected. So what you get from that is basically classical dynamics, but with quantum Boltzmann statistics. And then you have zero-point energy. You have incoherent tunneling described well by these ring polymers evolving in time, but you can't get a quantum phase or some interference. Yeah? So this is okay for condensed phase systems, because big condensed phase systems at high finite temperatures, these quantum coherences usually are not at all, they decohere quite fast. And what you have is really this type of tunneling and zero-point energy. You can calculate vibrational spectra. For example, this is a molecule called the Zundel cation. This is this method that I said here, when you calculate quantum nuclei equations of motion compared to classical nuclei equations of motion. So you really have the right positions of these OH stretch peaks with respect to experiment. But this method, because of certain approximations that we do, they predict peaks to be too broad. So you can't really get a good resolution of these. We went further and we made these approximations a little bit better by attaching fancy colored noise thermostats to some of the equations of motion. I think these details don't matter here. But the point is that currently this type of theories give you a spectrum that looks more or less like this. These dotted lines are the positions that you have in experiment. And well, I mean, it's doing quite well. You have not the same accuracy that you would have in experiment, but it's good enough. And you can calculate it. This is an isolated molecule. You can calculate these things in the condensed phase, these red and green lines. So these are systems with 120 or 200 watt molecules. You can calculate the full vibrational spectrum here, and you get these spectra that look quite okay. And then just as a last thing, so there's another So in this path integral formalism, you can do several approximations. I was talking always about molecular dynamics on them, even for vibrational properties in approximations now. And another approximation that we use to calculate, for example, rates of reaction, so another time-dependent property, is the ring polymer instanton approximation. So these are really instantons that we have. But in this case, so these instantons are, again, a steepest descent approximation of the action. So you truncate an expansion of the action at second order. And the different thing that we do here is that, again, we discretize the path. And then you end up, again, with these ring polymers. So you end up with a ring polymer potential here. And you have to find a saddle point in this extended space of the ring polymer. So the instanton will always exist below a certain crossover temperature, which has to do if you have a harmonic barrier here with the imaginary frequency at the barrier. And you just optimize these you find the saddle point of that, and that is what gives you the action. So then you can calculate the rate. This part here doesn't matter. This is a harmonic approximation because you truncated your action to the modes that are perpendicular to the reaction mode. And then you multiply here by the minus S, the action over h bar. And S over h bar you can show is given by, again, this 1 over nkt. And then the potential, this ring polymer potential at the saddle point position. So this is the same. And then you can calculate reaction rates. So that's what we do. So again, the game is just finding that. And you can get a reaction rate that includes zero-point energy, tunneling, corner cutting. And in this case, it also includes coherences, but only these that you truncate at second order, so harmonic-like. And then it really matters for some systems is, again, that porphyrine molecule from the beginning. Let's first play the game of calculating vibrational spectrum. This harmonic approximation, this is an easy thing to do because every mode is then independent. You find every vibration of your nuclei to be independent. And then you have this really strong signal, which is the stretch of these NH groups here inside the molecule. But experiments were very puzzled by that because they had never measured this peak. So this is the experiment really in the same frequency range. People had already looked at the system. Maybe harmonic approximation is your problem. So let's calculate the spectrum from the Fourier transform of the dipole autocorrelation functions. It's an infrared spectrum. And that gives you something beyond the harmonic approximation, but here still making the evolution with classical nuclei. You see that you don't have a particularly good fit. So you see that this peak exists here in this dotted line. It doesn't exist in the experiment. And then if you do this time evolution with quantum nuclei, with all the harmonicities included, this is the answer that you find here in the bottom. It's a really good match with the experiment, actually. And this is something where this signal comes like that because of this delocalization of the hydrogens inside the cage. These are overlaid snapshots of the simulation. You see how delocalized they are. Not only that, if you look at the temperature dependence of these vibrational peaks, so this is the same NH stretch peak with temperature. If you do quantum nuclei, it shifts to the right here, so to the blue, to higher energies as you increase the temperature. But if you would just do the dynamics with classical nuclei, it has a very slight red shift instead. So these are completely different descriptions, so qualitatively wrong, even if you do classical nuclei. And the reason for that is that this NH stretch mode is coupled to a very low energy mode, which is this cage mode, this breathing mode of the cage of this molecule. And the cage mode is thermally activated at this temperature. It's not quote unquote quantum because the energy level spacing there is much smaller than the thermal energy that you have. But this NH stretch is quantized still. So if you do with quantum mechanics, what you have is a modulation of this potential in the transition. And this transition becomes larger because the potential becomes different, or the cage becomes larger at higher temperatures. But with classical nuclei, you have both modes not quantized, of course, and you can only just put thermal energy inside. So the only thing you measure is how anharmonic the bottom of this double well potential of this hydrogen transfer is. And then if it's so important for that, it must be important for rates. So we calculated also the rates of reaction of transferring these hydrogen atoms within the cage. And this is what we calculated, this instanton theory that I had showed in the slide before, in this experiment again for this molecule. And this is all with nuclear quantum effects, with tunneling included. And the tunneling enhancement factor here is a factor 70. So if I had not put that in, I would have an answer that was 70 times smaller than what I calculate. There is a temperature dependence of the rate, even though you are already in the deep tunneling regime here below 150 K. And this is because this is not just a simple double well potential. It's a very high dimensional system where modes are coupled all over the place. So the temperature dependence happens even though you're in the deep tunneling regime for this reaction of the hydrogen transferring, because you have modes that are thermally activated that couple to your reaction rate. So if you calculate the instanton, the energy where the instanton starts to tunnel, so the tunneling height under the barrier at different temperatures, it changes with temperature. So this 100K, this 150K, and this changes because of the coupling of this mode. And this doesn't matter because we don't have time. So with that, I actually come to the end of my talk. These are the people that did most of the work. This is my group there. There are PhD positions open in my group from 2020. And this is the funding and computing resources that I have received. And thank you very much for your attention.
So we have time for questions. So,
have you showed that the vibrational spectrum of water agrees with observations once you take into account the quantum nature of the nuclei?
Yes, it does. Yes, I didn't show here, but yes.
Because I didn't see. So
Yes, yes, yes.
So if I produce this
yes. Yeah. But you know, for a single water molecule, you can also solve exactly the quantum Schrödinger equation. So in principle, you don't need any of these for that. Nah? The idea is just to show, you know, we can do that, and we can do much, much larger than that, where you wouldn't be able to actually solve the Schrödinger equation there. Yeah, so.
Are there other ways to try to solve or try to compute this passage without discretizing?
I don't know. Not in our area. I mean, for us, discretizing is really nice because then you know, then the mapping is that you end up with several replicas of a system, right? And this is easy to do. That's easy for us because actually nuclei are not very quantum, you know. So I mean, if we would do path integrals for the electrons, I don't even want to know what that is, okay? Because the electrons are very, so what I'm neglecting here, for example, I'm considering all my particles to be distinguishable. So I'm not considering indistinguishability of particles because it doesn't matter in this case. But as you go low and low in temperature, or if you have electrons, for example, obviously, you have these effects. And then you can also do path integrals, but you have an exchange term that is very difficult to converge. So. But you can't, because the perturbation, there are ways to do perturbation theory. So, so perturbation theory, the problem is that you have very high dimensional systems, right? And you typically cannot truncate the perturbation theory at second order. So the couplings, if you have any type of an harmonic potential, are really, really pronounced, even beyond second order. So quickly, you get to a situation that you can't do anything. So there are methods like vibrational perturbation theory of second order that are perturbation theory there, vibrational self-consistent field, which is an MP2-like approximation for nuclear degrees of freedom. They exist, but they don't work as good. I mean, you can't deal with them for really, really high dimensional systems. Yes. Yeah.
I have a question. In this last molecule that you have the proton transfer, so why do you need coherent tunneling for it also to be described correctly?
In that case, I don't think you need coherent tunneling at all. It's just included there. Where you would need that is to look at tunneling splittings. So for example, this theory can also do tunneling splittings. But then they are only really pronounced at much lower temperatures as you really go towards zero temperature, and then you can see them, and that's then a coherent effect. Yes.
So for the time transition, you need the instanton configuration.
Yes.
How do you find the instanton configuration?
Yeah, you do a saddle point optimization on a multidimensional potential energy surface.
So it's numerical.
It's numerical. Yeah.
Any further questions? Okay, so let's thank the speaker again. Oh yeah, there are refreshments upstairs.
Before going to